Hello, we have a population growth problem here. Pretty common application of exponential growth. So the 1990 population of Arizona was 3.7 million. All right, so that's our initial value, growing at an annual rate of 1.7%. Okay, so we've got two questions that we're going to be answering. What will the population be in 2005? And what is the doubling time for this population? So we're looking at, I start with 3.7 million in 1990. We want to know at this rate, if I grow at 1.7% a year, what I'm going to end up with. Second thing, doubling time for this population. So this is just a benchmark that people who study this, if I was in like urban planning, if I were a city manager, or someone in government, and I wanted to know, do I need more roads, more buildings? What's going to be the strain on my water supply, that sort of thing. A common benchmark to kind of talk about things like that is to get your doubling time. All right, so let's get started. So first of all, is this linear or exponential? It's giving us a percent growth rate, not a fixed amount added or subtracted a year. If I go up by the same amount every year, I'd be linear. If I go down by the same amount every year, linear. But instead we've got this percent multiplier, so we're exponential. All right. Choose and label variables. So these are what's changing in this situation. Well, the two things that are changing are going to be the time, and I think we'll stick with x and y for this for now. So x would be my time in years. So what am I measuring as far as time goes? I'm measuring the years from 1990 to 2005. So that's changing. And then my y is going to be my population. And if I started with 3.7 million, I'm going to leave it as 3.7 million. I'm going to leave it in millions. Sorry. 3.7 million is actually a constant. That's not going to change. That's just what we start with. And my annual rate, that's not going to change either. That's also a constant. So population in millions. Okay. All right, starting value for the population. Well, they gave us that it starts at 3.7 million, so I'm going to put that in. 3.7 million. We'll say millions of people, just to be even clear. All right, now our growth factor is 1 plus r, which is this percentage turned to a decimal. So that's a connection to what we were doing before. We need to write this thing as a growth factor. Well, okay, if I have 1.7%, I'm going to divide that by 100 to get rid of my percent sign. So I've got 1.7 over 100. I'm going to move my decimal twice. So 1, well, let's see here, 17, 1, 2. So 0.017, that's my rate when I turn this to a decimal. And then remember, it's a growth rate, so I have to be above 1. So I'm going to add 1 to that. So 1.017, that's going to be my growth factor. Alright, so now it says write an explicit formula. This is what we were doing on the quiz, or some of you may have missed this. This is new. We wrote explicit for the linear, and we did not do that for the exponential. We just wrote the recursive. But now we have the capability of doing this now. If you missed it, I'm going to show you how right now. So the format is B is going to be my initial value. And where this A is, that's going to be my rate or my factor I'm going to grow or decay by. So just like in y equals mx plus b, how you're going to put your starting point is going to go here in your y-intercept. And your slope is going to give you the constant difference. You're going to go up or down. So, if I start with if I pay $100 to join the gym and then $10 each month, my $10 each month is going to go here for my slope. So this is repeated addition. So this is my rate here as my slope. And this guy is repeated multiplication. So just like my slope I'd put here, my growth rate I put here on the x. Okay. So let's see here. So I'm just going to fill it in with the information I have. So I'm going to start with y, which is going to be my population, is going to be determined by this function, 3.7, and I'm putting that in my b slot. That's what I start with. Okay. Times 1.017 to the x power. And this is my time. Okay. So again, here's my growth factor, goes here in this A, and my initial starting point goes here, the 3.7 million. This thing is still the y-intercept on your graph if you were to graph this thing. And like the slope, this thing is my rate. Okay. How many years have passed from 2005 to 1990? Well, 2005 minus 1990 is just 15 years have passed. All right. So I'm going to count 1990 as year 0, and 15 is where we're gonna end up. And I'm just gonna plug into the function. Now, if I look up here, it's always good to kind of keep in mind what's what. 15 years is my information I'm using. I want to know the population in 15 years. And you can imagine that that's something that if I'm a city planner, if I'm a government planner, if I'm, if I'm a business owner and I want to project what demand for my product will be, how many more stores do I need, that kind of thing, I want this kind of information. I'd like to know, well, what's a good guess at the number of people that will be in my state in 15 years in this case. Okay. So if you look at this, I'm just going to match up the units. I'm not going to put it here because these are millions of people. I'm going to put it here because it's my time. So y equals 3.7 times 1.017 to the 15th. And we've seen this sort of thing before, like on the quiz, etc. Okay, not quite so formally, but. All right, so looking at this, I'm going to get out of there, my graphing, and I'm just going to type this thing in just the way it appears. So 3.7, and then my growth factor is 1.017, and then I'm raising that to the, what power is this going to be? 15. Because basically what I'm saying is that I'm going to start with this initial value, and I'm going to multiply it by 1.017 15 times. Okay. All right. And there we go. I've got 4.7644. So y equals 4.7644. And that's in millions of people. Okay, I mean, that may not seem like a lot, but when you look at this thing, right, this is about 1 million more people in Arizona